the ground state of hydrogen. Part A, calculate the most probable value of the radial distance r from the nucleus for an electron in the ground state of the hydrogen atom. Now, as we have seen, the radial probability density function P1S of r is basically 4r square divided by a0 cube multiplied by exponential e to the minus 2r over the Bohr radius. And how did we obtain this? We have the psi1s wave function. Multiplying its absolute square with 4 pi r square, we obtain the radial probability density function. So that was our result. So if I take a derivative of this probability density function, derivative of psi p1s of r with respect to r and set it equal to 0, what will I find? The extremum point of this function. So first to take the derivative of 4r square with respect to r, that gives us 8r divided by a0 cube exponential minus 2r over a0. Next, take the derivative of this with respect to r. That will give us minus 2 over a0 multiplied with 4r square over a0 cube. It will be 8r square over a0 to the fourth power exponential minus 2r over a0. It's equal to 0. Okay, so in 8r over Bohr radius cube parentheses, we have e to the minus 2r over a0 minus r over a0, the Bohr radius, e to the minus 2r over a0. So I should have taken the exponential out as well. So this gives me 1 minus r over a0 is equal to 0, which means the extremum point is when the radius is equal to the Bohr radius a0. And if I look at the other solution, which is r is equal to 0 solution, r is equal to 0 solution gives us the minimum point. So this is the maximum point. How do I know which one is minimum, which one is maximum? If you substitute r equals to 0 here, you will have 0 probability. If you substitute r equals a0 here, you will have 4 over a0 e to the minus 2, which is non-zero. Therefore, this will be corresponding to the maximum. This solution will be corresponding to the minimum of the function. Part B, calculate the probability that the electron in the ground state of hydrogen will be found outside the Bohr radius. Okay, so the probability of having r greater than a0. This will be being at a radial distance between a0 and infinity, the probability density function 1s of r dr. Okay, so I'm counting the probability of being at r equals a0 plus dr plus 2dr all the way up to infinity. That's probability of being outside the Bohr radius. Okay, so if I go back and substitute my radial probability density function, 4r square over a0 cube, 4 over a0 cube is just a constant, so it will stay outside of this integral. And this will be an integral from a0 to infinity, r square e to the minus 2r over a0 dr. So what I'm going to do is I'm going to call this e to the minus 2r over a0 dv, and I'm going to call this part u. Okay, so I will be doing integration by parts. So integral of u dv is equal to uv minus integral v du. What is this? This is integration by parts. Okay, so I remind you of this trick in calculating the integrals, integration by parts. And if we apply this here, we have 4 over a0 cube. Now u was r squared, so what is the integral of e to the minus 2r over a0 dr? That is minus a0 over 2 the exponential. So this will give me uv, which is minus r squared a0 over 2 e to the minus 2r over a0 evaluated between the bore radius and the infinity, and then I need minus integral v du, which will be plus a0 over 2. So that's the v. Now the du part will give me, if this is u, du is 2r dr, so that will give me 2 integral a0 to infinity r e to the minus 2r over a0 dr. Okay, so this will give me 4 divided by a0 cube. Now I have evaluated at infinity, this will give me 0, evaluated at a0, so I will have 0 minus, it becomes a plus. If I substitute r equals a0 here, I will obtain a0 cube. So this will be a0 cube over 2 e to the minus 2 a0 over a0. And then I have plus a0, the 2's will cancel, times this integral. Now this time I'm going to call this part dv and this part u. So integration by parts again. So in a0 parentheses I have uv, which is the integral of e to the minus 2r over a0 dr. So that will give me, now including this a0 here, it will give me minus a0 over 2 exponential, and then I have the function u here, so it's u times v, u times the integral of this, so it is minus a0 r over 2 exponential minus 2r over a0, which should be evaluated between a0 and infinity. Then I have minus integral v du, so minus with this minus sign from the integral of dv will give me a plus, so this will be plus a0, since v is a0 over 2, so this will give me plus a0 over 2 integral a0 to infinity v du, so it's going to be e to the minus 2r over a0, because u was r, du is dr. Okay, so this is 4 divided by a0 cube. Then I have a0 cube over 2 e to the minus 2. Then here I'm going to get evaluated infinity 0, evaluated at a0, this minus sign will become plus, so 0 minus minus, it will become plus. So I will get a plus a0 cube, because I substitute a0 here, a0 cube over 2 e to the minus 2. Then I have a plus a0 multiplied by a0 square over 2. Then I have to perform this integral, which gives me minus a0 over 2 e to the minus 2r over a0, evaluated between a0 and infinity. And this part will give me a0 cube over 4 e to the minus 2. Why? Because evaluated at infinity, this will go to 0, so 0 minus minus will become a plus, and substituting a0 here, I get e to the minus 2. So a0 cube over 4 e to the minus 2. So a0 cubes will cancel, and my answer will be e to the minus 2 parentheses. Then I have 4 over 2 plus 4 over 2 plus 1. So that gives me 2 plus 2 plus 1, 5 e to the minus 2. 5 e to the minus 2 is 0.677. So I see that the chances of being outside the Bohr radius is 67.7% probability. Okay. So let's write it this way. This is 67.7%. All right, so we're looking at the ground state of hydrogen. First, we want to know the most probable value of radial distance r from the nucleus. We use the radial probability distribution function, which is obtained by using the psi1s wave function absolute square 4 pi r square, which is obtained from a transformation from a volume density function to a radial density function. Now, taking the derivative with respect to r, setting it equal to 0, we find the extremum points, r equals a0 and r equals 0. If you substitute 0 here, probability is 0, that's the minimum. R equals a0 gives us a finite value, that's the maximum we're looking for. It's a single Bohr radius. As we have discussed in the previous lecture, the most probable point here is a single Bohr radius. What is the probability of having the electron in the ground state of hydrogen to be found outside the Bohr radius? Well, for that I have to integrate between a0 and infinity the radial probability density function. So that means I have this integral from a0 to infinity of 4 over a0 cube r squared e to the minus 2r over a0 dr. By using integration by parts twice in this integral calculation, I get 0.677, 5 times e to minus 2 as the answer. That is 67.7% probability of being outside the Bohr radius.